Hello, welcome to lesson 5.2. Today we're going to learn about perpendicular bisectors and angle bisectors. So by the end of the day, I hope you will be able to say, I can understand and use properties of perpendicular and angle bisectors to solve problems. Now, if we first start with this problem, it says draw the shape that is made by drawing all the points 3 centimeters from a given point. Now we're just going to sketch it because I don't have a ruler here, but if I go out 3 centimeters, that might be there. If I go 3 centimeters out here, it would look like this. If I just keep going around and doing all the points that are 3 centimeters away, what it will look like in the end is a circle. That's a pretty bad circle, but my radius is going to be 3 centimeters. That would be the shape that's made from drawing all the points that are 3 centimeters from point A. So now if we want to find the shape that's made by drawing all the points 1 centimeter from a segment now, so let's just say that's about 1. So we can draw all of these points, and then we'll draw all the points down here. Those are all 1 centimeter away from the segment AB. Now it gets a little trickier on the edge, so we're just going to go 1 centimeter from that point, and it looks like it's going to be rounded. So we do the same thing here. One student in class said it looks like a hot dog, or maybe a track um, that you run around. But that's the shape that will be 1 centimeter away from AB. Now I want you to think about the shape that's made by drawing all the points equidistant from A and B. Equidistant means equally distant. So if I picked one point, this point here would be the same distance from A and the same distance from B. The midpoint will also be. And if I keep drawing this, let's see what this creates. Notice how that's going to create a line. And that line is going to cross right in the middle. So it's going to cut AB in half. And it also looks like it's going to be perpendicular. So a perpendicular bisector is the set of all points that are equidistant from the two vertices. And that's what we have here. Every point that's the same distance from A and B will be on that perpendicular bisector. Now if we have an angle and we want to draw all the points that are equidistant from those two segments, that one's right in between, that one's in between, and we can keep drawing them. And in the end, if we connect them, if they're equally distant, then that's going to be an angle bisector. So a point on an angle bisector of a triangle is always equidistant from the two sides of that angle. Alright, so now we're going to look at circumcenter and incenter. I'm going to pull it up here for a second. Let's look at circumcenter first. Now we did this in our constructions chapter where we looked at these centers on GeoGebra. Now if I have an obtuse triangle, notice how my circumcenter is going to be on the outside. If I have an acute triangle, my circumcenter is on the inside of the triangle. However, if it is a right triangle, that's 89, let's get it closer, 90.06, that's pretty close. If this is a right triangle, my circumcenter is going to be on the hypotenuse. These two smaller sides we call legs, and this third side is called the hypotenuse. So if we draw this, oh, my computer's slowing down here. All right. All right, I think I got a hang of this now. Now these two sides are going to be congruent. So this is going to be the midpoint. And notice how this is going to be the diameter. So each of these sides is going to be the radius. So if I wanted to find the radius of this, they call this radius a special name. They call it the circumradius because it's the radius when you circumscribe a triangle. All right, now if we look at incenter, if I have an obtuse triangle or an acute triangle or a right triangle, it doesn't matter. The incenter is always right in the middle. All right, so now if we continue on, this question asks, find the circumradius of a circle that circumscribes a right triangle with legs 5 and 12. So first we can draw our circle. If it's a right triangle, we know that it has to pass, the hypotenuse is going to be at the diameter. And so now we just draw the other two sides. And this is going to be our right angle. So now we just label the two legs. Since this is the hypotenuse, that's not a leg. These are the two legs, 5 and 12. So now we have to use Pythagorean theorem to find our hypotenuse. 5 squared plus 12 squared is equal to c squared, or 25 plus 144 is 169. And if we square root 169, c is equal to 13. So if 13 is our full diameter, our circumradius would be half of that, or 6.5. Now if we look at all 4 points of concurrency, right here, now I can pull this up and you can see that I have all 4 points here. I have circumcenter, centroid, incenter, and orthocenter. Now, as I move these around, if I make an isosceles triangle like this, notice what happens to all these points. They all line up right in a row. And if I move it this way, they're going to line up again when this becomes isosceles between having these sides being equal. But if I wanted them to be on the same point, I just lower this until I have an equilateral triangle, and all 4 of my centers will be at the same point. Now, when I bring this off to the side, there's one center that isn't in a line. Notice how the incenter doesn't form a line. If I draw that line, notice how that the orthocenter, centroid, and circumcenter always stay, we call it collinear, on the same line. So if we look back, this has a few questions. Euler's line is that line that connects those 3 centers. Which 3 centers does it pass through? Well, there's the circumcenter, the centroid, and the orthocenter. When are all the points in the same line? Remember when those all lined up? That was when it was an isosceles triangle. And when were they all the same point? When I shrunk it down to be an equilateral triangle. All right, I think that's all the information you need to do your homework. Good luck.